Today we want to look at non-radial models. Non-radial models. The word radial carries what idea? Radial. What sort of idea does radial model carry? Anybody?
I think it brings to mind proportional from the origin.
Okay. And what does that practically mean? When you say a model is radial, what does that practically mean?
Okay. I think practically it means that if you increase the inputs by 20%, the output should also increase by 20%.
Okay, good. So the adjustments of the resources, they must be of the same percentage. That is what radial models capture. Now, the DEA model that you've learned so far, they can be radial or non-radial. But the original study of the DEA actually propounded the radial because at the time, there was no knowledge that there was going to be a non-radial model. The radial models are concerning proportional reduction in the input or proportional augmentation of the output. Now, the word proportional means that you maintain the ratios of the inputs and the outputs at the same time. And the commonest radial models are the CCR and the BCC model. Now, in an input orientation, output orientation, non-orientation, which of these can you use to distinguish the CCR from the BCC? Which of these can you use to distinguish the CCR from the BCC model? Which of them two? Suppose you want to distinguish between the CCR. Emily?
That would be the input-output orientation.
Why?
The non-orientation. Okay, so because if you are doing just so if you are doing two inputs or two outputs, that one it will be difficult to distinguish the CRS from the the CCR from the BCC. But if you are doing non-orientation, that's you have both the input and output, then you'll be able to see the difference.
So the radial models have been used for years, but then the radial models have got some disadvantages we come to. The non-radial models, they don't look at the proportions in the resources and the outcomes. They disregard the proportion, the mix, because they are all trying to reach the frontier, but the pathway to reaching the frontiers are different. And we shall delve deeper into this. Some of the non-radial models are additive and model of Chance, Cooper, Golani, Sayford, and Stutz. I think this was in econometrics. The Russell measure of Fair and Knox-Lavelle. The weighted additive measure of upper ratio et al. The Lavelle-Pastor measure, okay, in 1995. The enhanced Russell graph measure of Pastor et al. The directional Russell measure by Fukuyama and Weber. The weighted range directional distance model of Shen et al. The range adjusted measure of Cooper et al. The slack-based measure of tone. The dynamic slack-based measure of tone and Chuchi. The geometric distance function of Patella and Tanasolis. The directional distance function of Chambers et al. And the hyperbolic distance function of Fair, Groskov, and Lavelle. We are not done. Also, the bounded adjusted measure of Cooper et al. The additive slack-based measure of Shen and zoo. The connected SBM of Evkiran, Tone, and Twitwi. The multi-directional efficiency of Bogotov and Hugard and Asma Tab, and the extended and non-radial directional distance function of Tavanna et al. So you can see as it stands that we cannot learn all these non-radial models. We can't. But the principle is what we are going to learn so that when you are reading the others, you can appreciate them even more. These models are necessary. These models are what you're going to be using. Today, we are going to look at one of these non-radial models. Why are they necessary? Because the radial models, even though they are good, and we say they are good because radial models are unit invariant. They don't depend on the unit of measurement. Even though they are good, and with a radial model, you can also get a single efficiency score. 1. The problem is that they assume proportional reduction in the inputs given the outputs, or proportional augmentation in the outputs given the inputs. They ignore non-radial slacks. Now, there are slacks in the radial. Take note. The radial, there are slacks in the radial measure. And there are also slacks in the non-radial measures. But, so even though it is trying to consolidate the slacks in the radial because it's a radial measure, it ignores the non-radial slacks. These non-radial slacks, if on the input side, these are the inputs you should have reduced but have not reduced, and therefore they become excesses. Or the outputs you should have increased but have not increased, and therefore they become shortfalls. And such are wastages. And when there are these wastages, the managerial efficiency computed by the radial models will not capture the true efficiency measure because it's neglected these factors. So to ignore non-radial slacks is not a joke. It's a big problem. And that is the essence of our study here. So how do we capture these slacks? Well, the non-radial models are very useful. Why? Especially when the idea is to improve both the inputs and the outputs. If you are trying to optimize the slacks, straightforward by including any information in the slacks into the objective function without a proportional adjustment of the inputs and outputs. And that is a unique feature of the radial model, of the non-radial models. So what we are saying is that the non-radial models, particularly the one we are going to look at, what they do is that they take the slacks that have been neglected by the radial guys, and they don't just incorporate the slacks or tell you that they are slacks, but then they infect the efficiency score. They add that slacks that was ignored. They now add it to your efficiency score so that your efficiency scores are penalized. They are penalized with the identified slacks. And because of that, when there are targets, either on the horizontal or vertical sections of the graph, those targets become, the targets would have been infected under the radial models. But now you get a correct target under these non-radial models because it incorporates what? Slacks. The other thing is that the non-radial models are more discriminatory than the radial models. What does that mean? What does it mean to say that the non-radial models are more discriminatory than the radial models? I'm going to be asking you these questions according to the way your names are written. So first I see Jerry. Jerry, what do we mean to say that these non-radial models are more discriminatory? What does that mean? Jerry, are you there? Yeah.
So it means that they are able to change proportionally their input and output.
No. Albert Benson.
Doug, I think because they can work on both the inputs and the outputs, it doesn't really matter which of them you're trying to adjust. So it essentially can target either the inputs or the outputs.
No. Albert Kofi.
Look, I don't want to guess. I don't want to guess.
Doc, can I tell you?
You mean you don't know?
Yes, Doc.
Okay, Jerry, back to you.
So we can say that they are specific in terms of their variables.
No. Chris Duncan. Chris Duncan, are you here?
Yes, Doc.
Go ahead. It's for this class. Once you are on the call, you are called. What does it mean to say that they are more discriminatory than the radial models?
I think the non-radial models are able to categorize the score specifically instead of just generalizing.
No. Kenneth Kwedo.
I think it's because of the ability to distinguish between efficient and inefficient DMUs.
That is why they are what?
Discriminatory.
What do you mean by that? Explain what you mean.
So they
Now, Sir Godwin.
Doc, I think it's able to look at the very small details between firms. And so if that be the case, other models like the radar models may miss. So being able to identify those very small details within the firms, then it's able to prioritize which firms or DMUs to call efficient.
What do you mean by small details?
So for example, like say the microdecimals.
Are you sure? I like the way you say microdecimals. Oh, good. I like the way you are mathematicalizing your answer. No. Emily.
Okay. So it has more discriminatory power because, for example, if you take the efficiency scores, so radial models might give you a certain efficiency score, let's say 80% efficient, but when you use the non-radial model, it can give you about 60 because they are incorporating slacks in there. It reduces the efficiency they will give to a firm if the firm has slacks in there, if you're using the non-radial model.
Is that good or bad?
It's good because it shows the actual efficiency of the firm. since the slacks has been incorporated.
That's it, guys. So when we say that the non-radial have got more discriminatory power, that's what it means. When we say they are more discriminatory, what it means is that they cut down the efficiency scores. They don't force you to be efficient. They try as much as possible to reduce your efficiency. So you may get more efficient firms under the DEA model than under the non-radial models. You get more efficient firms under the radial than under the non-radial, because the non-radial is incorporating slacks, which is more inefficiencies. And because it's incorporating more inefficiencies, your actual 100% efficiency comes down. And this is good, because imagine all your companies are efficient. And then you go as a consultant to go and tell the management that based on your analysis, all the banks are efficient. The management will now say, okay, thank you very much. No money. No money. You won't make money if you are seeing more efficiencies. But once you identify that, oh, out of the 100 companies, only 2 were efficient. Now they are going to chase you to help them what they can do to become efficient. So when a model is more discriminatory, it's better than the one that is not discriminatory. Albert Ben-Susan, do you understand?
Yes, Doc.
Explain. What do you understand?
Okay, so we are saying that the non-radial models essentially force our efficiency scores to be within a certain factor range. So let's say 0 to 1. Traditionally, the radial model would characterize the DMU as efficient, even though there might be slacks. But the non-radial model will essentially force the model to make sure that if there's any inefficiency, it throws it up. So when you're comparing the efficiency of a radial model versus a non-radial model, the same DMU using a radial model would say it's efficient, but in the non-radial, it would say that it's inefficient because there are certain factors that the radial did not consider.
Excellent. Kenneth, do you realize that when you understand the thing, it doesn't matter what you read online? You fully understand the thing, so you're able to explain it in your own words. There is an additive model we mentioned. We should have gone for that. It's one of the non-radial models, but we're not going for that. Why? Why are we going to discuss a slack-based measure of efficiency by tone? It's because the existing additive one is non-radial, all right, but it's not unit invariant. That's one. The additive model is not unit invariant. Oh, what do we mean by a model is unit invariant? What do we mean, Godwell? That a model is unit invariant.
Like unit invariant means that we are able to put in different inputs and outputs regardless of their unit of measurement. So maybe we have labor, which is measuring maybe number of labor. We have maybe oil, which is measured in some quantity, or some. We have something like capital, which is measured in currency. So irrespective of all these currency, the number of people we can put all into the model, it doesn't matter the units, so it's unit invariant.
Perfect. Excellent. Now, the other disadvantage of the additive model is that it doesn't give you a final efficiency score. So the efficiency score, just like the radial, it does not incorporate or doesn't give you a total efficiency score. And so we cannot use that. The SBM is a champion in this case because it's unity variant, it's monotone, it gives you a final efficiency score, and it incorporates slacks. Look at advantages. when you are writing your paper, those are exactly the same thing that you're going to say, about that. That you are mentioning these things, for people. You are trying to explain it to them for them to understand. Okay. Now, let's get to the SBM running. Like I indicated, the people behind the SBM is basically Tone, 2001, published in EJOR. Tone, 2002, published in EJOR. So we are going to look at the input-oriented SBM, the slack-based measure of efficiency. And Guy, I'll show you also why most other models eventually come and adopt something related to the SBM. One, the input-oriented SBM is measured for a particular DMU naught that is consuming Xij amount of input I producesYrj amount of output R by solving the following input-oriented SBM efficiency model for a particular DMU, and we are assuming variable retention scale. Now watch it carefully. I'm using I for the input here. The rho is the input-oriented efficiency score. To get the input-oriented efficiency score, we need to minimize this objective with the intention of finding the following decision variables: the lambda, the Si negative, and then the Sr positive. The Si negative is the input slack. The Sr positive is the output slack. So you take 1 minus 1 divided by M. M is the total number of inputs. So if the total number of inputs are capital, labor, and deposit, then it means that M equals what value, Chris? M is equal to what value?
One.
No, I said if the total number of variables, inputs are capital, labor, and deposits, then what is the value of M?
Capital labor, then 2.
No. It means that M is rather 3. M is rather 3.
Capital labor deposit, okay.
Now,
Sure.
you have SI, which is the slacks. Take note. So if the slack in that particular input is 0, remember that we will need this to do the computation. We look at an example. So let's say that the slack is 2. Okay, the slack is 2. And we also have a situation where the input of that particular DMU is 4. And there is another input. So this was for input X1. Okay, so this is all for input X1. I can give you this in an example. Okay, and this is for DMU. This is input X2. And that's for DMU A. And then with this input X2, it generated a slack of 1, okay, with an input of 5. So, and there are 2 inputs here. What will be the efficiency score? What is going to be the input-oriented efficiency score for DMU A? All of you should calculate for me and let me see. What will be the input-oriented efficiency score for A? Remember, you have the values. And by the way, when I said slacks, these were the slacks. Okay, the SI. These are the slacks. And then these are the inputs. the inputs of the firm under evaluation. Are you guys working? Emily, are you working?
Yes, Doc.
Albert Kofi, are you working?
Yes, Doc.
Jerry, are you working the answer?
Yes, please.
Who is going to be the first to give me the answer? What would have been the efficiency score? You may have finished, but you don't know that you're finished. Who is?
Okay.
Yes, Emily.
Okay. Prof, I got 0.65.
I think you might be correct, but let's see. 0.65 is what she got. So what you're going to do, you're going to substitute the value. So you get 1 minus 1 over 2 because the number of input are 2. Then you put into
Yes.
bracket. You have the first input, which slack is 2, divided by the input itself is 4. So it's 2 divided by 4 plus
Yes.
1 divided by 5. So at this stage, you can find the LCM. The LCM between 4 and 5 is 20. So once you get a 20, 4 goes into 20. 5 times 2, 10. That's at the top. Then 1 goes into 20, 20. Sorry, 5 goes into 20. That is 4. 4 times 1, 4. So you have 10 plus 4, giving you the numerator to be 14 divided by 20.
0.65.
So half of that, half of the 14 is going to be 7, and half of the 20 is going to be 10. So now you have 1 minus 7 over 10. The LCM is 10. 1 goes into that is 10, so you have 10 minus 7. And 10 minus 7 is 3 divided by 10. Is that it? Is that what you got?
No. No. I had,
You got 13 over 20.
so, Doc, it will be.
Oh, yeah.
Okay.
So you get half of this, that gives you 20, and then you have, what gave you the 13? The 13 is a numerator, isn't it?
Yes.
What gave you the 13?
So you do 1 minus 7 over 20.
Yeah. So what gave you the 13? 20 minus 7, isn't it?
Yes, 20 minus 7, yes.
All right, okay. So you get 13 by 7 by 20, and that gives you 6.65. So that is, I'm just showing you how you calculate the input-oriented efficiency. You have to do this in your exams. You have to do this in your thesis. That's why I'm demonstrating a bit of that too, but I'll do it better on the output side. So this is an input-oriented efficiency score subject to the following. Now watch it carefully. I have not brought the less than or equal to because I want to incorporate the slacks. And once the slacks are incorporated, the whole thing is set to equality. You know this from linear programming. So the weighted sum of the inputs of all DMEs. Watch the word of all DMEs. When we get to the super efficiency, I'll be talking about the weighted sum of input of the other DMEs. Very important. Okay. Plus the slacks equals the input of the DMU under evaluation. Remember, you have plus the input slacks and then minus the output slacks. And then this left here is the convexity constraint, whereas this blue one is a non-negativity constraint. Once you get this done, you have formulated input-oriented efficiency. The most important thing, guys, is this one here. Now, let's go to the output-oriented. And by the way, the idea is to find the following decision variables. So a DMU is said to be input efficient if the score is 1 and all the slacks are 0. Not just the score is 1, but the score is 1 and the slacks are 0. That is a true SBM efficiency.
Okay, Prof, please question.
Yeah.
If we go back to the constraints. Okay, so last week with what we did, if we were doing input orientation, then we will have something attached to the input side on the right-hand side. That's either the theta or the phi for the output. In SBM, there's nothing of that sort.
You got it.
Okay.
Very, very good observation there. Okay. Now, in the output-oriented case, this is the same thing, but you can see that the output-oriented, I've taken the reciprocal. And by taking the reciprocal like this, I'm able to put the score between 0 and 1. That's all. If I had not taken the reciprocal, the scores are going to be above 1, which is what it's supposed to be, isn't it, for output orientation?
Yes.
So take note. Now, how do you get a score? You just add the sum of the slacks to the 1. Whereas in the input orientation, you subtract the sum of the slacks from 1. Guys, it's important you understand this model that we are doing. This is a serious model, and you want to understand the interpretation of it. Because we shall do the output orientation in my practical one, I'm not going to ask you to calculate it. And again, coming back to your point, Emily, you can see clearly that you're going to see that most of the time, the constraints are the same for input and output orientation. They are the same. The only thing that changes is the objective function. One is maximized, one is minimized. One, you are adding the slacks, which is output orientation. The other, you are subtracting the slacks from 1. So that is it. Look at the way you formulate it carefully. But, as usual, if the rho is equal to 1, it means that the firm is efficient together with the fact that the slacks are 0. All the output slacks have to be 0. Now, input slacks may be non-zero in an output orientation. So take note. But for you to be efficient, the output slacks will have to be 0 in an output orientation. If the input slacks are non-zero, that's okay. But the output slack must be 0. And even though we are putting the efficiency score between 0 and 1, once this one is 1, 1 divided by the rho is 1. So that matches it. Then there is the non-orientation. Now, if you check this non-orientation here, it is using an optimization problem here. And the optimization problem that is using is a minimization. It's using a minimization, which means that it is trying, even though it's a ratio, it is trying to minimize the entire ratio. Now, one way you can minimize the entire ratio, there are 2 ways. Who can tell me one? What is one way you can minimize a ratio?
No, by reducing the denominator and increasing the numerator.
By reducing the denominator, good, or increasing the numerator. Are you sure?
No, by reducing the denominator. One, by reducing the denominator and increasing the numerator. For example, if you have 3/5 and you increase it to 6 and you reduce it to 3. So to
You
2.
increase what to 6?
You increase the numerator to 6 and you reduce the denominator to maybe 2.
What will happen?
Yes, it will increase the ratio.
Okay. So you increase the numerator, reduce the denominator. Now let's go to the numerator. How can you increase the numerator? What is one way of increasing the numerator? Is by reducing what?
The slacks.
Exactly, the sum of the slacks. So when you reduce the sum of the slacks, you can force the whole of this part here to be what? You can force the whole of this to be what?
0.
0. And once you force it to be 0, now eventually you have 1 minus 0, and then you have been able to have it. So have it in mind, you are minimizing the sum of the slacks there. Now, at the same time, what can you do to the denominator? You can do what to the denominator? You can increase it, isn't it? The sum of the slacks. When you increase the sum of the slacks, whatever it is, given whatever is up there, you can bring the whole ratio down. Do you agree with that? You guys agree?
Yeah.
All right.
Yes, we agree.
But there's more. So my question to you is, why is the whole thing called minimize? This is where the intelligence comes in. Why are we using minimize then? We are using minimize because the denominator, which should be increased, is, or the output slack, which should be increased, is in the denominator. In other words, if this thing should be brought up and raised to the power -1, it will be on the same level frame as the numerator. Okay, and in that case, maximize will work. Okay. But we know that when it comes to here, we are already trying to minimize. We know that when you minimize this part here, the whole of this ratio is going to be towards 1. Okay, so this part here has got the minimization. This part here has got the, look, 1 is constant. So let's not think about 1. It's constant, it's untouched. So it is a sum of the slacks that we're interested in. If you reduce this value, given the constant 1, the numerator will go up. And if you increase this value, but this value is in the denominator, so when you bring it up, it's raised to the power -1. Now, if you increase that, but when you bring it up, it will be minimized if you should reduce it. Okay. If you bring it up, it's just like this numerator. And when you reduce it, the whole thing gets to 1 as well. That is why you have a minimization. Do you understand, guys? This is an exam question. If you don't understand, you ask. Okay. The other thing you also notice here is that the inputs and the outputs are just 1. In other words, we are not distinguishing the types of input and the types of output. Take note. What are the types of, so we are not distinguishing in the output section, we are not distinguishing desirable output and undesirable output. It's just output, S. And then, of course, the constraints are the same. As you can see, the constraints are just as they are. Okay. Of course, if you want to explain it, the non-oriented SBM implies that the slacks are 0. Both the oriented and the non-oriented, okay, they are not linear. Or whether it's oriented or it's non-oriented, they are all ratio. The objective function is ratio. One way you can remove the fractional programming is by linear programming. And I'm not going to show you, but you should go and check it in the book on how you can linearize it. That is just the way you write it. You're only talking about how you write it. And to do that, this is a way of linearizing. It's just like the original CCR model that we spoke about. You set the denominator. Okay, watch here. You set the denominator here equal to 1. And then you will address only the numerator. You will minimize the numerator. So here, we are using a tau to indicate that we are minimizing the numerator. And we are setting the denominator equals to 1. There's some slight manipulations that have gone on here, but that's okay. This is how you linearize it. Okay, now you set it, there are all no fractions anymore. And so we can go ahead and add this. But there's something you see here. Emily, what do you see in the constraint?
Okay, so I think 2 additional things I'm seeing is the t greater than 0. And also, so here, the XIO and then RO are having t attached to them. And we are setting it to be greater than 0.
Very good. That is it. So it's very important to recognize that t here is a positive value because of the ratio. Because of the ratio that has been linearized. Okay. Now this is a non-oriented one, the undesirable output. Now what do you see about this one compared to the previous one? There's a clear-cut difference between this one and that one here, at least the objective function. The objective function. What's the difference between this one and that? And when you check this one too, there's a slight problem with the formulation. Do you see a slight problem with the formulation? At least compared to the others. You see that compared to the others. Look at these others. And then check this. There's a slight problem. I just want to be sure whether you can identify that. Jerry, have you identified that?
Yes, Doc, partially.
Tell us.
So we have an exponent now. So we have, yes, we are being introduced. Exponents are being introduced into the constraints.
Where is the exponent?
The y exponent g.
Y exponent b and g.
Yes, g and s exponent g plus.
Oh yeah. I'm not talking about that. I'll come to that. I'm saying that there's a problem with the formulation.
Doc, even though it's output orientation, we are using minimize.
It is both input and output. Oh. You see the
okay.
Yeah, the ability to identify problems in models is important. It's still non-orientation.
Okay.
But there's something. It has to do with the information on the left-hand side of the quote.
Okay, okay.
It didn't come.
What didn't come?
Okay, so we are saying, okay, you brought the left-hand side rather to the right-hand side. So we have the input being equal to, what is that, the summation one there?
Not exactly.
So the slack has been, for the first one, the slack is being added to the constraint instead of subtraction.
Oh, it's the same thing. The numerator, you subtract the input slack from 1. The denominator, you add the output slack to 1. There's no problem there. Let me tell you guys, the problem is that you wrote row star not. Okay. This row star not should be on the left-hand side alone. It shouldn't be minimized.
Mm-hmm.
The minimize must be affecting whatever is here. And then once you have a star here, it means the star has gotten a value which is an efficiency score. So once you have the star alone must be on the left-hand side. You're not minimizing the star too. You are minimizing the row, but not the star. And so we go back here. You see, here, you have the star equals to the minimize. The minimize is for the function. The minimize is against the function, the ratio. Whereas the score is the one on the side. So this minimize shouldn't be here. It should rather come to the right-hand side before the first bracket. Does it make sense?
Yes, Doc.
Yes, Doc. So that means that
I will
the
write
star,
models like this, and then I'll mix some things and tell you to identify 3 problems with the model. So it's important you are recognizing things. Yes, go ahead, Jerry.
Doc, so it means by the star, it means the value has already been evaluated.
Correct.
So you cannot. Okay.
So you cannot minimize it again.
Okay.
It is a function that you are minimizing. Therefore, the min or the minimize should be on the right-hand side. Very important. Now let's come back to the difference between this one and the one that is oriented. This one is non-oriented. The other one too is also non-oriented, but the difference is that we have incorporated undesirable output. How does that change this from the previous one? How does it change? Very important though. Godwell, tell me one.
Doc, so this one is incorporating both inputs and outputs. Even in the outputs, I see there YG and then YB, good outputs and bad outputs.
That's good. So you are talking about the objective function, right?
Yes, please.
So what he's saying is that objective function, we have a good and a bad good. The good is the J, the bad good is the B. We have both of them. What else do you see in the objective function? That wasn't in the previous. Should I show you the previous? This is a previous one.
No.
There's something else about the S. You see,
No, it's S1, S2.
you have only
S1 and S2.
S, but you have to explain what that means, not just mentioning it. What is the point here?
Okay, so S1 refers to the total number of outputs or the good outputs. So total number of good outputs, and then S2 will be total numbers of bad outputs.
Yeah. So the 1, if you are to carefully look at it in this context, the 1 and the 2 could have been changed to what?
J and B.
Excellent. It could have been changed to J and B. So that you have one big one divided by S1 plus S2 will become 1 divided by SG plus SB. So that's a number. Take note. It's not a slack. If you don't take it, you confuse it with a slack. The slack is always in the numerator. The slack is always in the numerator. And there's a problem with this. Okay. The slack is always in the numerator. And there's always a plus or a minus. Okay, there's always a plus or minus, depending on whether it's an input slack or it's an output slack. Okay, so enough of the objective function. Let's go to the constraint. What is the change here in the constraint?
Okay, so we have one additional constraint.
What is
That's
that?
the output constraint is now 2, where we have one for S1 and then another for S2. So for the good output and then for the bad output.
What is it about the bad output that you see similar with the input? And what does that mean? Godwell. Guys, you see that I'm delaying here because I know what really happens when you are presenting yours. What is it about a bad output that makes it share some similarity with the input? But what does that also imply?
Okay, so you see that with the bad output, we have plus the slacks. Also with the input, we are saying plus the slacks. So in both instances, we are saying plus SI naught, and in the YB, which is the bad output constraint, we're also saying plus
What is the
SR
implication?
plus. So it means that for inputs, we are adding back the slacks. To be efficient, you have to add plus the slacks. Bad output also, we'd have to add back the slacks.
Why?
W then come.
Prof, is it because you also want to reduce it?
Reduce what?
Okay, so just like the
No, I'm
input,
saying reduce what? You say it. What?
the
But why? You said it. You want me to take it as it is?
no.
I should
Okay,
decide
so
on what the it is.
yeah, we want to reduce the, okay, so if let's say the bad output has a certain number, we want to reduce the number of bad outputs, the quantity of the bad outputs. That's why we incorporate the slack so that it shows the efficiency that we can be improved.
That is why we incorporate what?
Like we add back the slacks to it in calculating the efficiency
The same way we add back the slack
when
for
we are
the
doing the
input.
input.
But
Yes.
why? Why? What would the implication of having the slack in the input section mean? If the slack there is positive, then it means that that particular input is having some input excesses, isn't it?
Yes.
It means that the inputs have not been fully utilized. Now, ideally, you want to reduce the input.
Yes.
Yes.
But now here you have some input being left. That is why ordinarily the slacks will have to be 0 there. The same thing with the bad output is bad, it's pollution. You want to reduce that pollution. And yet there is a pollutant. Okay, so what your goal is to reduce that pollutant is of course it's an undesirable output. It's a byproduct. Now, if it is a byproduct of the good output, that's a whole different ballgame. Okay, because then it is exhibiting weak disposability. But in this context here, it's being treated just like the input. So you don't want it. You don't want that negativity, that externality to appear. So you are adding it to it. You are adding it because your goal is to increase it. The output, the reason why it's minus is because the output is something you want more. You want more. So if you get less of it, you don't want it. So you want more of the output. Sometimes it might sound a little bit like it's tautological, but that is not. You want more of the output, and that is why you got to take the minus. Otherwise, you have output shortfall, and you don't want a shortfall in output. You want good number of output, not a shortfall in the output. So understand how the two of them behave. The input is moving in the same direction as the bad output. Yes, Emily.
Prof, please, you made mention of the slacks of the inputs, the input slacks being unused inputs.
Yes.
A little bit, is it overused input, as in inputs that were used that should not have been used?
I never mentioned unused input. I said input excesses. Yeah, you can call it unused. Input excesses. Not overused. Unused.
Okay.
Or let me put it this way. Yes, unused. Because here you have this input that you are supposed to minimize, you're supposed to use. Remember that the idea is that as you are using them, it's going away. When you are using it, it's depleting. You are reducing it towards zero. So if you still have a bit of that from what you should have used, that becomes excess. And this excess is not something you want to keep. They are slacks. They are supposed to be zero. So that is why in the non-negativity, the slacks have also been set to be 0 or more. If they are more, well, the more means that it's possible. It's possible for them to be positive. But then they are not supposed to be positive if you want to be efficient.
Efficient, okay.
So if you have input excesses, that is bad. So what the slack is trying to do is to minimize those excesses. See the thing? The slacks, the SBM model is trying to minimize the excesses. And that is why you can see that in the objective function, you are subtracting them from 1. Because the 1 is like where I have reached. You know, and I'm taking anything away from it. And I hope that whatever I have here is 0. So that whatever I take from, I eventually have this. We'll be calculating. So that you see the power of this thing. So I just want you to know that the behavior of the input is the behavior of the output in this slack-based non-oriented model. Okay. Now that you've understood the mathematics, of course, these are all the information. Yes.
Please, the slack represents the excesses. And
yeah, you got to tell me which slack you are talking about here.
I'm talking about the plus, the one with plus.
The one with plus does not represent.
Plus the first one, SI minus.
Okay, plus the SI negative.
Negative.
Yeah, so just the input slacks.
The input slacks. So I'm wondering what will happen, how we shall interpret it when it is minus. Because if you are minimizing when there are excesses and it is being, that is when it's added. When it is subtracting and we also have the same minimization. I don't know.
When it is what? It is a negative value. Do you see it here?
Yes. Now, then please come to the positive one.
This one?
Yes. Can you distinguish between the first one, the positive one, and the
there's a typo. It's not supposed to be positive. Hold on. It's a very good observation. Okay. So in here, this value B plus is supposed to be B minus. This one here. Okay. is supposed to be B minus. This one here. Supposed to be B minus. Now, again, let me just go back quickly. When I take you back here, when I take you back here, you will notice that that is the same B minus here. Okay, the same B minus. And then even in here is still B minus. Okay. And then even up here in the objective function is B minus. I don't know, goodness me, why I did not. So again, this is supposed to be B minus here. And this is supposed to be B minus here. Does that make sense, Godwell? Go and
Yes,
check.
sir.
Go and check all your models also, so that you are not found wanting. So that's it. That's how you're supposed to recognize these things every time. How do I even remove this? All right. So that is supposed to be B minus, but then it's still being added. Jeffrey, just to go back to your point. You're still adding it. Yeah, you're still adding it. Okay. Now, this is still fractional, so you can still convert it using the Chance-Cooper transformation to linearize it into a linearized linear programming problem. Okay, we know about that already. And that is a point of discussion here. You can formulate it into that. I'm not going to do that because I already did that for the one that didn't have the undesirable output. So you should be able to use that same principle here. Now we are going to take an example to run the slack-based model. We shall do it all in R. This is exactly how you would have executed it also if you were running it in R. So, looking at this data set, are we doing input orientation?
Sorry, I think the recording has stopped though.
Oh, really? No, we are still on.
Okay.
We are still on. Look at my name, you see there. Okay. One person is off the radar, right? Kenneth, okay. So, looking at this, is it an input orientation or an output orientation? Chris and Albert Kofi, one of you should give me that answer. Is it an input orientation or output orientation? Chris and Albert.
Yeah, Doc.
It depends.
So we have deposits and loans. Sorry, deposits and loans as inputs, and then output as investments. So it's input orientation.
The moment you started it, I knew that you have to eat. And Jerry, what's the name? Chris, what do you say? It depends on what?
Well, it depends on what you are defining as the output, because sometimes loan can be
what?
Output, so
Check the
it can be
values.
an output, and deposit can also be depending on the option that is, or that the researcher is taking.
Masa. It doesn't depend on anything. So, okay, so which one would you have made an input? Or you are saying there is no input, there is no output?
No, there is. If
so which one is there?
There is an intermediary approach also. I'll take deposit as an input and then loans as an output.
No. Even I could have changed all of this and called it X. I could have just used X, Y, and things like that. That's all. I would have used that. Where you don't even know what variable it is, It could have been anything. I could have used deposit, I could have used capital, I could have used labor, I could have used anything. But what if I use A, B, C? So imagine this one is A, this one is B, this one is C. That's what you should think about. Yes, Jerry, help him.
Doc, we have one input, two outputs.
Why?
In that case, the one that is 111 is the orientation that we are going with.
No. That is not the orientation we are going with. Jerry, continue.
Deposit is an input. So, for example, people come in and deposit.
So what orientation are we going with first?
So this is output dominated.
Why?
Because you have more output than input.
Oh.
That the input has been normalized.
That's all. That's all the reason. If the inputs are 111, which means you have been normalized, there's nothing more to check its efficiency again. That's all. And how do you know that that is an input? Because given the others can never be an input. And you must have an input. Loans can never be an input. Investment can never be an input. You always want more investment, want to give more loans. Because you know that giving loans will lead to the benefit of interest. But the main advantage is that one of the variables has been normalized. Now that variable which has been normalized, that variable is the one that you are not going to consider. Now in this case, the advantage is that you know the names of the variables, loans and investment, and you're never going to reduce them. So even if you know that you can increase deposit, you also know that you can decrease deposit. So in this context, deposit will have to be decreased. All right, and if deposit has to be decreased, then it is an output orientation because we have dealt with the input already. So the rest is to focus on how do you maximize the output. This is how you execute these things. Okay, so now I gave you this data set. You should plot them. You should plot them. Has any of you been able to plot them? Any of you? Okay. So this is a data set. Try and plot them. If you scatter plot them, you know how they will look like. Okay. Let me see if I can scatter plot them for you. But you should learn. Let me see. Actually, you can do it. We've done it before, haven't we?
Yes, Doc, we've done it before.
So if we have done it before, you should be able to do it again. So if you go and scatter plot it, you get something like this.
Yes.
Doc, I just have a question. So far, what I've read on input and output orientation regarding banking, right? They sometimes characterize loans as inputs, depending on what the researcher is looking at.
So what was the researcher looking at for it to be?
So they characterize the loan interest rather as the output. And so if it's not specified,
yeah, you said depending on
directly from.
Well, for your information, loans are always an output. That's why I'm saying that what you are saying, it depends on, you said it depends on, you haven't told me yet what it depends on, but I'm telling you that loans are always an output. Loans are always outcomes of
Yes, but in the production approach, I know in the intermediation approach, yes. But in the production approach where you are
in
using
the production approach, loans is not on the bank side. You are looking at loans from the perspective of a branch of a bank. And from the perspective of bank branch, loan will be an input because people just collect the loans. They bring the loans to the branch. Remember, there's a difference between bank efficiency and branch efficiency. So at the branch efficiency level, loan is an input because people give the loans to the bank branch. The bank branch now uses that loan to combine it with other loans from other banks. And then they are able to now get the rest. They're able to get the loans out, which at that time is at the bank level. But whenever you are talking about input and output, please don't bring intermediation because it can be any other industry. You see, what we are looking at here is general DEA industry. And so you must have a knowledge on what defines an input. An input is something that is being consumed. An output is something that is being generated, generally. Generally. An input is being transformed into an output. That's another way of looking at it. All right. So, guys, by looking at this, which firms are efficient under the DEA approach? Which firms are efficient? I've added the numbers here. Oh, what is just shaking like that? Okay. Which firms are efficient under the DEA? What is the name? Godwell. Which firms are efficient under DEA?
Dr. GAAP, those on the frontier.
Again.
GAAP, those on the
Perfect.
frontier.
So these are the efficient firms under the DEA. And therefore, the inefficient firms are BNF. How did you determine, or how do we determine the efficiency? Okay. Now, we're going to run this thing in R for you to recognize something very, very profound. And this is very, very profound. First of all, remember that efficiency can be determined as the distance to the frontier divided by the distance to the firm. So if I want to find the efficiency of B, for example, okay, the distance to the firm is at 4. The distance to the frontier is at 10. So what will be the efficiency score of B? What will be the efficiency score of B, Albert Ben-Susan?
So to the frontier is 10, to B is 4. So that's 4 and 4 10 to 40%.
No. You didn't use the definition. Albert Kofi, what is the efficiency score of B?
Dog, the distance to the frontier is 10. And then the distance to the firm the distance to the frontier is 10. And the distance to the firm is 4.
It's 10 over 4, so it's actually 2 point.
Yeah.
2.5.
Is that a correct measure of efficiency?
No.
Distance to the frontier, that is.
This efficiencies that you just mentioned, Albert Ben-Susan, you said 2.5. Is that a correct measure of efficiency?
I mean,
it's greater than 1.
It's greater than 1, yeah. So
is that a correct measure of efficiency, I'm asking?
No, it's not.
Why? Why is it not? Emily, is that a correct measure of efficiency?
No, Doc. Its efficiency is supposed to be between 0 and 1. So
that is wrong. Is that a correct measure of efficiency? Godwell.
Doc, that's the output. Okay.
No, Doc.
Did you also say no?
Yes, please.
Why are you guys all failing today? What is it? If you were in class, I would have let you all stand.
It's output. Sorry, it's correct. It should be greater than 1. Output. Yes, it's correct.
Hey, what is happening today? This is dangerous academic discholarship. Please, wherever you are, stand up. Wherever you are right now, don't sit, stand up. Just so you know, I have stood up almost 6 times whilst talking to you. In one of them, I was just kind of jogging whilst I was talking with you. Stand up. Stand up. It will help you. It will help you a lot. Yes, it's very important you stand up because your brain power needs a stand up ovation. So this is 2.5. It's an output-oriented measure, which is good. It shows that the firm B is what?
Inefficient.
It's inefficient. And that is a DEA language. That is how DEA will measure efficiency. Now, the way the slack is going to measure efficiency is different. It will measure efficiency using the steps. It's going to calculate the steps. Watch it. Remember, it's not going radial from the origin. It goes from the firm. But the whole idea is to reach the frontier. Remember, some will go this way and will reach the frontier here. Some will go that way, reach the frontier here. Some will go that way, reach the frontier here. You know, some will use different means to reach the frontier. So let me just take a. So whilst you're at B, you can reach the frontier this way. You can reach the frontier that way. You can reach the frontier that way. You can go in the DEA way. And then you can also reach the frontier that way. And then that way. Okay, and that way. And then that way. And you can use several means to do that. Now, what the slack-based measure is doing is using both horizontal and vertical movement. Finish. To reach the frontier. Now, horizontal movement would have hit this part of the frontier for B. It would have hit this part of the frontier, which means that at that part, it would have generated what?
Slacks.
And because it doesn't want to generate slacks, it will go this way after hitting this part. But then this one and this one, which one is closest to a slack version? Is it the C part here or the E part?
The C.
It doesn't like itself to be closer to a slack area. Put that in your mind. That is a slack-based measure. It doesn't like to be in the vicinity of slacks. And because it doesn't like to be in the vicinity of slacks, it tries as much as possible to stay away from there. That is why it decided not to even get to this section in the first place. But once it gets to that, it sorted out its pathway to go to this. It gets to that point. And at that point, it is still it's stable. And when it becomes stable like that, if you can see, you now want to measure the steps. So it's not going to calculate steps. How many steps do you need to get to this section? How many steps from the point 4 on loans? How much increase in loans does it have to have? Does B have to have? Remember, the loans are in millions. And right now, it's producing 400 loans. So how many more loans?
I think an additional 6 more. Yeah.
6 million. And then when it gets to that 6 million, it will do what to the investment as well?
Increase the investment from 4 to 12. Sorry, from 4 to 10.
By how much?
So by 6 again.
6 million again. So you see, it's using steps to reach the efficiency. Now, these movements are what we call slacks. These movements are called slacks. So you now move 6 positive slack, 6 positive slack. And so when you get to the output section, okay, you remember that's SR. Remember that SR plus, okay? That SR plus, they are going to be 2 for the output. So each one will have its what? Y. Then the other one, the second SR plus, that one too will also have its Y. So the actual Y are here. So that is 4 and then 4. Then you have 6 here, and then you have another 6 there. And you remember that there is 1 over S, and the S stands for what? 1 over S. The S stands for what? Do you remember? I'm talking
The
about
number of outputs.
number of outputs. So here, the S will be what?
2.
2. Exactly. So now you're going to now do the 2 and then multiply it by these things. And whatever you get, you will add 1 to it. And that will give you the output efficiency score. It's beautiful. But then, if you can remember, the output efficiency score, I wrote it as 1 over row output star. Yes, Emily.
Okay, Doc, so it means that the reason why A was not considered was the same reason C was not chosen.
Exactly.
That's the A and C. Okay.
Exactly. Because they are in the vicinity of slack. And this is very important, guys. If you can understand this, all of you are going to do non-radial models. You should be able to crack that code. You are staying away from slacks as much as possible. Now let's go and run the codes. And then we'll come to the reality of this. So you're going to run these codes. So this is the R. I'm going to take my data set, and it should do the same. And I'm going to just copy my data set and put it there. So I'm going to show this data set. First, you need to load your library DEAR. Okay, so let me load that. And then run the data. To see the data, just highlight D1. And this is the data. Do you guys see the data? Guys, I will encourage you to be doing this along, because that is the only way you can master this. There's no other way. Albert, Kofi, are you with me?
Yes, Doc.
If you don't follow these things systematically, you will be at a loss, and it will also not help you when you're on your own.
Yes, Doc.
Now, you will see that whenever I write the codes, I give a bit of instruction. Emily was struggling never to give instruction until she stuck. Emily, no boy.
Yes, Doc.
And then sometimes she goes to the code and then she says, hey, what did I even write? Because you've forgotten the instruction. So whatever you write, this code is actually telling you how to import the full data set using clipboard from Excel to R. Okay. What about this is.DEA data? What it is saying is that you want to check whether this data is actually the right way you have organized the data for it to be accepted. Now, please take note that you must always have the name of the DMU first, then all the inputs, after that, all the outputs. That's how you should follow. Take note of that. Okay. Then, this will now check if the data is of a class needed for DEAR. When you run this, it will tell you false, as you can see here. Okay, it's telling me false, false at the bottom. What does a false mean? It means that the data is not of the class needed by SBM analysis or needed to solve in this particular package called DEAR. Okay. What next? Now we have to force it and make it acceptable. So we now rewrite the name of the data set and say, this time I want you to reuse the function called read_data and ensure that inside this data frame, the first column is the DMU name. So DMU equals to 1 means that's the first column. Even though the column name is bank, it doesn't matter. You can just make it DMU1. NI should be the number of inputs. And in our case, the number of inputs, as you can see, is deposit, that's 1. And then NO is the number of output. So you check the number of output is loans and investment, that's 2 output. So you specify that. But apart from this, there are other things you can specify. For example, imagine that one of the outputs was undesirable. Let's say you had non-performing loans, and it was a third variable. Okay, let's say you had non-performing loans, and it was a third variable. Then you are going to say that the number of outputs here is 3. Let's assume that the last column will be the non-performing loans, the last column. Then in that case, you have to come and then type here. This is very important. Type comma, and then put here UD, undesirable underscore output. And then you type what number, Emily? What number will you type here?
Dot 3.
3.
It is the last one. Yes.
Exactly. So you type 3 because that non-performing loans is, which is undesirable output, happens to be the third of the output. Not the third of the variables, but the third of the output. So you indicate 3. Now, suppose you have some non-discretionary output. You can put this there. Okay. Now, this means that which of the output is the non-discretionary?
The first output.
Yeah, the first one.
The first output. And this means that which of the output is non-controllable?
The second.
You got to know the meanings of each one of these and when they are needed. And once you do that, before you know you are done. Of course, you can do the same thing for the inputs. Very important, what we just done. Very, very important. Let me just undo this. But in our case, we know that this one is the situation. So you just run this. It will tell you some warnings, but don't worry. Once it's gone through, it's gone through. The next is to now run your DEA efficiency. Now, in the DEA, the DEA efficiency is called model basic. Model basic. So I called it DEA. DEA. You may have gotten yours separately, it doesn't matter. But you can change it even to here. It's better this way. So DEA means the efficiency score coming from the DEA. The D1 is the name of the data frame. The orientation is output oriented. That's why it's OO. If it is input oriented, it will be IO. Okay. And if it is non-oriented, it's NO. And then if it is directional or other things, you can specify. The returns to scale is constant returns to scale. In this very data, all of them are located in the same production possibility set, the same corner. So they are all exhibiting constant returns to scale. Okay. But you can also change this constant returns to scale to variable returns to scale. Then you run this. Once you run it, you can just highlight this to just show the efficiency score. Okay, you can show the efficiency score with command 8. Okay. And this is it. You can see that just as you all calculated, the output efficiency score for B is actually 2.5. Exactly as we saw it. Now, you will notice that A is efficient. A is efficient. Now, if you can remember the graph, let me take you back a little bit to the graph. Let me just go here. You can see that A is truly efficient. B is inefficient. Okay, let's go back to the result. You will notice that C, D, E, they are all efficient. C, D, E are all efficient. When they come to the graph, C, D, E are all efficient. But you can see that D is in the wrong place. So what mistake is DEA doing here? Albert. What mistake is DEA doing when it comes to D? Are you here?
There's not a yes, though. No,
Albert
for the
Bensusan.
flag.
Mm-hmm.
Not accounting for the slacks.
It's not, when you say it's not accounting it where? I want to understand. Anybody? It's not accounting it where?
Doc, it's not punishing D for having slacks
Yeah, how do we know it's not punishing?
because it gives it an efficient score of 1.
Good. So it's not accounting it where, which I asked, means that it's not accounting it in the efficiency score. Please note, DEA still knows that this guy is exhibiting slacks. And you're going to see the results very soon. But it did not account it. It shows that, yeah, D has slacks, but it didn't incorporate that into its efficiency score to penalize it. So understand that it doesn't mean that it doesn't know. It knows, but it's not capturing that in its efficiency score. That's key, in its efficiency score. Now, this efficiency score is output oriented. I can take the reciprocal here, okay, and then I can just show the score in an input, in a less than 1. This is how it would have been. I just decided to do that for doing sake. But you can show a summary of the first one where it shows the output-oriented score. Okay. This false here. In fact, later on, you should change it to true and export it to Excel. It will go straight to your working directory. Sometimes your working directory is your My Document. So the Excel will be populated there. And then you can go and see all the results. But I want to show you the results here. It's a lot. As you can see here, it's shown a lot of things here. So look here. Okay. It has given you the efficiency score in an output-oriented section. It has given you the slacks. It has given you the slacks for the deposit. There's no deposit slack. There are some loan slacks, at least for Jane. So it didn't give you a lot of slacks. The output for the investment, there are some investment slacks, and so many other things are here. The lambdas are here. That is those that were used as peers. The target are also there. Okay, shall look at that. And then as you can see, the returns to scale is constant for all of the firms. And the references are also there. Okay. Like I said, you can export this and rearrange it. Okay. And I'll show that very soon. Now, if you want to get a result in a data frame, this is a result in a data frame. So you can see that here, I have the efficiency scores bigger than 1, as you can see here. I have a series of questions I'm going to be asking you. And then I have the same efficiency scores, but, by taking the reciprocals and bringing it to below 1. Now, let's run the SBM. So that was a DEA, output-oriented. Let's run the SBM. So you can see that here, the SBM, the model name is called model_SBM EFF. The same output orientation, returns to scale is constant. Run this and show the scores. So as you can see, these are the scores. Now, the thing about the SBM, straight away, you can see that it automatically puts the scores to below 1, even though it's an output oriented. It automatically puts the scores to below 1. So in fact, it was part of the reason why I decided to put the scores for the DEA to below 1 so that they are easily comparable. Okay, so now, if you want to now, because it put the scores already to below 1, we don't need to take the reciprocal. Okay, so in taking a reciprocal, I just didn't take it. I just took gave a name to the reciprocal. And again, you can show the summary of the results here. I'm not going to do that. I'm rather going to show the efficiency scores in a data frame. So watch it. This is the efficiency score. And you can see now I'm comparing the two here. What do you see? You will notice that the DEA score and the SBM score are the same for each firm, except for firm D. Do you see that? Except for firm D. So for firm D, Bank D, you see that the SBM efficiency score is 50%, but the DEA said it was efficient, which means that the SBM has done what? Who can tell us?
and punished it for the slacks.
Good. Now, how was the slack incorporated in the score of the SBM for it to get this 0.5? We'll come to that. We'll come to that because that's the beauty of this. But of course, you can see that this is it here. It is clearly in the free disposability section. It is written inefficiency, mixing efficiency. As a result, it must go up here. Then you also have this F. What is so strange about the F? What is so strange about the F?
I think it's saying that even though it was already inefficient, it was still punished.
Exactly. So these are firms that are technically inefficient and mix inefficient. And therefore, the mixing efficiency. Now, when you go to the graph, let's go and see F. Who can use the graph to tell me why it was still punished? Well, when you look at the graph here, you see that that is where F is.
Yes, Doc. So when you look at the graph, you can see that for the if you were using the radial model, where it hits the efficiency, where it hits the frontier, is still in the free disposable line. So even if it was moved to efficient, it will still have been there. Will still have been slacks in there. Yeah. So that's where the punishment is. So where it hits the efficiency line is where the issue was.
Good. But then it's still inefficient. DEA says it's still inefficient. But how does the SBM still punish it further? That's my question. You see, SBM moves in a horizontal and vertical fashion. So if the SBM has gone horizontal fashion, it would have hit the slack at even a lower level, isn't it? That's where the issue is. It would have hit the slack at the lower level, which means that at this section, because the slack for the DA would have gotten to is this, but then the SBA would have created more slack there. Therefore, it recognizes that no, it has to go this way. Don't hit this section, rather move all the way here to get to that portion. And that portion will mean that it will now experience the slacks better. Or better still, it will now, the slack will still now better reflect in the efficiency score. And you will see that we'll calculate that for F very soon. And you see how this was done. Now, we will come to super efficiency. But for now, let's go back here. Okay. And now check all of these. This is the overall results, which I've decided to bring here for discussion. So what do you see here? Just as we said, you will notice that for the F, both of them under DA and FBM, they are all inefficient. Now, let's look at the slacks. Okay, these are the slacks. I have highlighted red the slacks. Now, by the way, the first one is always the SBM, and the second one is always the DEA. Okay, so when you check the efficiency, even the efficiency score, you will see that the first one here is SBM. The second one here is DEA. Always take note. When it comes to the loan slacks and the investment slack, the first is the SBM, and then the second follows. Now, what do you see about the slacks between the SBM and the DEA? Total slacks, what do you see generally? There's an obvious thing. Chris, sometimes I want to be sure that people here are here. What do you say about the total slacks?
Hello?
Yes. What do you see about the slacks? Godo, what do you see?
Look, so the SBM has more DMUs having slacks than the DEA.
Exactly. That is an obvious pattern that one can actually dictate. That's the obvious pattern, guys. If you don't get that pattern, that's it. This is key. This is key. That's the first thing. So you can see that how many slacks were identified?
So at least 1, 2, 3, 4 of them.
Check carefully. How many slacks in total were identified?
5. 6.
6 slacks, isn't it?
Yes, sir.
6 different slacks were identified in this data set by the DA, by the SBM. And how many were done by the DA?
DEA 3.
3. So you can see that slacks have been much identified by one method than by another method. And because slacks have been identified, they will affect the target. So look at the SBM target. Okay. You will notice something about the target. You will notice, take for example, the target for F. Okay. F, the output were 8 and 3. That is 8 million loans, 3 million investment. But they are supposed to have what? 10 million loans, 10 million investment. When you combine these two relative to the actual, you will see that we are talking about 9 million of loans and investment that this particular bank is supposed to pull up. 9 million. But when you look at the DEA slack at the target, okay, when you look at the loans are 8, and the target says it should go to 12. So it means that you need to have a slack of what?
Drop 4.
You need to have a shortfall of 4. And then when you
Yes.
look at the 3, okay, it's supposed to go to what? 6.
6.
So another shortfall of 3. You add a 3 to the 4, that is what? 7 million.
Yes.
But when you look at the slack base one, when you add the 2 together, that is 1 million, 9 million. So you can see that the slack base measure is telling Bank F to do more. There's a lot more to do. There's so much shortfall of output that is supposed to target. And that is one beautiful thing about the slack. The slack can allow you, can let you bring out the best in you because it will identify deep weaknesses in you for you to be able to pull up your weight. Very, very important. Okay. Now, we are going to look at the output-oriented SBM for F. Okay. How do we now get the score? This is how the score is. This is the way to get efficiency score. Remember, the efficiency score is not 1 over blah, blah, blah. It is actually the row star. So we're going to do this. This is a general one. Now let's do for F. So for F, you're going to identify, okay, 1 plus 1 over S. S is equal to what?
S is 2.
S is 2. Then it says that you should take the slack of each of the output divided by the actual output. So the first one will be what? The slack of each of the output divided by the actual output. For DMU F. For loans. To be what by what?
So it will be 2 over 8 plus 7 over 3.
That's it. 2 over 8 plus 7 over 3. That is what you have here. Guys, you should learn how to calculate this. And this what I'm just showing here now, that's exactly what you will show in your thesis to demonstrate to the reader. Now, of course, you must have estimated the model before you show this example for the reader to see that, oh, okay. Because you can't conjure the slacks. You know the why. You know the S, but you can't conjure the slacks except after estimation. Okay. It is after the estimation of the slacks that now you can find efficiency scores. Okay, let's drop it in. So this whole thing is going to be 1 over PF equals to, when you add all of this, you will get 2.29917. This is what you get if you use your calculator. But that is not what we are looking for. What are we looking for? We are looking for the actual efficiency score. So you cross multiply and divide. Okay. And when you cross multiply and divide, now you get efficiency score in proper between 0 and 1. And that is 43% or 44%. When you go to here, you will see that that was exactly the same value you had by the software. So you got to know how you can get efficiency score step by step after you've gotten the constraint sorted. By the way, in case you don't understand what I mean by how you get a constraint sorted, the slack would have been obtained from the constraint. If you check here, okay, if you check here, even here, the slack would have been obtained from here. So because this one is known already. So once the estimation is done, you can make this one the subject and you can find the slacks. Once you have the slacks, you can find efficiency scores. That is it. Okay. So that is how you find this efficiency scores. Now, the next thing is a general report on the findings. So let's go to the general report on the findings again. I've said almost everything, but then let's go through quickly. So first one, the DEA model, which I call the BCC model, found 5 DMUs out of the 7 to be efficient because the radial nature of the model didn't allow that slacks to be incorporated. Okay, so there were slacks. So out of this, it found 5 out of 7. And I think Godro was the one who mentioned all those 5 out of the 7. Okay. Which ones were not among? Albert Ben Susan, which ones were not among? Which DMUs were not found to be efficient?
So we had DMUs based on the original data set, DMU FP.
Let me give it to you here before you start lying.
Yeah, so DMU-F, so Bank F was inefficient, and Bank B was also inefficient. Based on this, and Bank G based on SBM.
But then it did say that some banks were efficient, So now SBM comes and says that no, there are some more banks UDEA have called them to be efficient, but they are not because they were exhibiting slacks. And those banks were D and G. D and G. So when you go to the data, you see that D, was actually said to be efficient under the DEA. That's why it was given a value of 1. But then the SBM says a lie. It's a lie. It's rather half. G was given a value of 1 here, but then SBM says it's a lie. It's supposed to be 77%. So clearly, SBM is more discriminatory in this context. Now, I've said it here. Which is more discriminatory? Is it the DEA or SBM? At this stage, I can call Chris, you and Albert Kofi. They're going to address this thing. Which one is more discriminatory, DEA or SBM, and why?
It's SBM.
SBM.
Why?
It's more discriminatory.
It's SBM. It's SBM because...
Explain all the reasons. 7 reasons.
Yeah, because... Yeah, so because it penalizes... It penalizes the DMUC which have slacks. So D and G were were efficient and they were penalized for having slacks. So that is one. Chris, can you continue?
I said 7 reasons. Is that the
Yes.
7 reasons you gave me?
Yeah, so I mentioned that it is the SBM.
I said 7 reasons. I needed you to say 1, 2, 3, 4, 5, 6, 7.
Okay, so one is that it's
No, you can't repeat because I gave you time, and if delayed, you are not talking anymore. I don't have to encourage you to give me the answer when you're supposed to give me all the answers that you're supposed to. Yes, you are teaching. You are not answering. You are teaching your colleagues. So you should know all the benefit, because at some point you finished. It's like you finished. Both of you are not talking again. So note that the notation of the optimal slacks are the same. Okay, the optimal slacks, okay, they are the same irrespective of what you do. They are always the same. This is very important. And the second point, we've already spoken about it. DMU-D has a full DEA efficiency score of 1, although it has an investment shortfall of 4. Okay, we saw that. Okay, and that 4, and in the case of DMU-G, it had a loan shortfall of 1.5. And yet those things were not incorporated. Remember, those values we are being mentioning here, they are not values from anything. They are values, these shortfalls are from the DEA result. They are here. Okay. We are talking about this one. Okay. Investment shortfall of what? Which one are we talking about? D and G, yes. Investment shortfall of 4 and 1.5. You have that. The 1.5 is this one. Is a gene. So this gene had that shortfall. And yet they were not captured. That's a point we made there. But when these slacks were taken into account, the SBM score came down to 0.5 and 0.77, as you can see. Similarly, the SBM scores for F was worse than those in the DEA model because of the existence of more output slacks. Finally, DEA efficient A, C, and E, they still remained efficient under the SBM. There was no problem with that. So that's it for DEA and SBM. How you calculate it is very important. Now let's go to the last thing for today, and that is super efficiency. Super efficiency was first generated as a means of differentiating those DMUs that are efficient. Take note. Super efficiency is for efficient firms. Efficient firms. Efficient firms. How do you construct it? How do you develop it? You construct it by avoiding that particular firm that can help span the technology. One of the firms can help to span the technology. I'm going to ask you very soon. And in that particular DMU under evaluation is excluded from the reference set. So let me show you a picture example. If you check here, the frontier is bounded using A, B, C, D. But then when you remove the C from the model, you can see that the frontier now becomes A, B, C prime, not C prime, A, B, D. A, B, D. A, B, D. So this is an input orientation, of course. So you can see that C would have been what? Would have been super efficient, because even when you remove it from the frontier is still able to be formed. If you remove it, the frontier can still be formed. And that is it. Now, of course, if you remove this guy, suppose I go here. Let me just show you. Suppose I go to A, and I move from A to C, and then move from C to that. you can still form what? You can still form a frontier. In fact, you can also move from A to D straight away, and B and C can be outside the frontier. But D cannot be outside, no matter what. And A cannot be outside, no matter what. But B and C can be outside the frontier. That is what makes B and C here super efficient. Very important. Okay. Anderson and Peterson, when they introduced this thing, they clearly explained it. Now, what I want to do is I'm going to take you back to our own. Tell me which DMUs would have been super efficient in our example here. Take your time and tell me which DMUs would have been super efficient under DEA. Emily.
E and C.
Is that final?
Okay, so A, E, and C, because A2 can be super efficient. If we cut from G to D straightforward.
So now you're adding more.
Yeah, so final answer is A, E, and C.
Is that your final answer?
Yes.
She's going to change it right now. Is that your final answer?
Yes.
Okay. What about the rest of you? Okay. So let's see. I'm just going to show you some of them. So that's it. You have A, E, and C outside. Okay, because you can still create a frontier and then they will be outside. Therefore, graphically speaking, they are going to be super efficient. Now we are going to prove that. Okay. Now, but before we prove that with our data set, let's watch how you formulate the super efficiency model under DEA first, before we come to the SBM. Now, if you check it, this is an output orientation model. What clearly shows a super efficiency? What distinguishes a normal DEA model from a super efficiency model in this example here? And please don't say, I see the word VRS super, so that's why. What clear?
Okay, Doc, I think one thing I'm noticing is in the constraints, in addition to the J is equal to 1, now the DMU under consideration, which is the not, is being excluded. So we have J not equal to the DMU under consideration.
Perfect. That's all, guys. That is all. Mathematically, that is all. So even if I don't bring VRS super, the way for you to know that we are dealing with that is that constraint. This one, that is what makes the whole thing. And you see that in all of the constraints. That's what makes this whole thing that. Very important. Very important. Okay, now, this is super SBM, but it is undesirable. Super SBM. Now, check it carefully. Now, in this very example, what is representing the slacks? Goddo, look hard and tell me. What is representing the slacks?
I think it will be the X cap and then the B cap
And then what other cap?
and then the Y cap.
Very good. So those are going to be for the slacks. So technically, when you look at do you see the difference between this one and our own? What makes this one correct? What makes this correct? Even though it looks like our own, what makes it correct? Because when we wrote that for our own, I indicated that our own was wrong because of something. What makes this correct?
I think the delta not, there's no star attached to it.
Sorry?
I think there's no star attached to the delta knot.
Exactly. So that makes this correct. So if you were to bring the star would have been on the left-hand side of the equation. Take note. Delta not star equal to mean. But watch it. That it is mean delta. Is mean delta equals to. So you can still bring the mean to the right-hand side. Because the whole thing on the right-hand side here is the delta. Okay, and again, what shows that this is a super SBM? What shows that this is a super SBM? And what has this guy done here that was unnecessary? Oh, by the way, what shows that this is a super SBM? Ben Susan. Hey, Jerry, is Jerry here?
Look, I'm here.
You have not been hearing from me at all. This is dangerous.
Look, I'm here.
What shows that this is a super SBM?
The J not equals to 0.
Again,
Down there, we have J not equals to 0. J not equals to 0.
J or J?
J for
Okay.
Jerry.
What is this person doing that is too redundant? So take note, one thing about the input is that you have the x1 greater than or equal to the input of the DME and the evaluation. You have the same thing, any of them. It was not necessary. There is one constraint at the very bottom that didn't show up. Which constraint is that? What constraint is that at the bottom?
No, I think that's lambda greater than or equal to 0 for all the I, J's, and then the R's.
Yeah. There's a non-negativity constraint at the bottom. Okay. So now let's go and run the super SBM in the software. So that's it. That's a super SBM. We are going to continue. So I'm just continuing as if we finished the previous one. I'm going to run the SBM. Well, I think I've run this SBM model. I'm going to super efficiency here. So I'm going to run, first of all, the DEA super efficiency. Okay, the one by Anderson and Peterson. I'm running that and I'm showing the results here. And because it's DEA and it's going to give me the scores above 1, I'm going to run this to give me the scores below 1. And then I'll show it and add it to the others. So watch it here. This is the DEA efficiency scores with super efficiency. Now, the original one is this. Okay, this one here. And this is a new one here. What do you say first about Fem A? What do you see? That makes super efficiency very good method. Looking at, oh, sorry, I was looking at DAE. It's here, this one. This first one against the DA super. What can you say about the result? Anybody?
Okay, so even though the DEA, the results were supposed to be 1 and above, the super DEA is showing us below 1.
Meaning?
Meaning that it's more than efficient. So yeah, even though like the efficiency was supposed to be 1 and above since it was output oriented, but it's giving us 0.97. That means it's over efficient.
Good. So which ones are being given from the previous DEA? Which ones are being given values of below 1? Which specific firms?
A and C and E.
Sorry?
A, C, and E.
ACE.
Okay. What were they before? That's my question.
They were efficient.
They were
So they had
efficient.
an efficiency score of 1, yes.
That is the most important thing you want to take note. If the firm is already inefficient, it is not touched by the super efficiency model. The super efficiency model touches only those that are efficient. But of course, not all those that are efficient will be discriminated against. The super efficiency model discriminates. But of course, it discriminates those that are efficient. It discriminates them. So that is what you see under there. Remember the DEA super efficiency. Okay. Remember this. We are going to go now to what do you call it? We are going to go now to, and remember that if we are to take the below one, that makes it nicer. The below one, now when you go to the DEA super efficiency here, you will see that they are above one. Okay, which clearly makes it even nicer. Because when you're above one, then it's enjoyable to say that you're super efficient. Do you guys get what I mean? Okay, so that is for this part of the result versus that part of the. So you can see that this one is truly 103 is truly super efficient, 117 is truly super efficient, 108 is truly super efficient. Take note. Now, let's run for the SBM. So I'm going to run the SBM model, okay, like this, and now put all together. So watch, now let's look at the DEA super efficiency, okay, and then the SBM super efficiency. This is interesting. Look at them too. And I'm talking about when the values are 1 and above, okay, 1 and above for super efficiency. So watch it. The super efficient for A is 103. The SBM brings it to 102. What does that tell you? In other words, it doesn't show it to be more super efficient. Do you see that?
Yes, sir.
It mixes. I'm telling you, I've tried this multiple times. It mixes. For example, this firm is inefficient. Inefficient. Okay. In the super efficiency model is inefficient, and this inefficient firm was now made what? Efficient in the super efficiency. Interesting. Now, this one is super efficient. It's still super efficient, but it was not made too much super efficient. This one and this matches. This was now super efficient, but it was not made too super efficient in the SBM. This is inefficient, and it was made efficient in the super efficiency. So what is happening? What are you observing? You're observing that the inefficient firms are made what? Efficient, whereas the super efficient firms are not made too super efficient. Do you see that? This is important. This is important observation for SBM super efficiency. But the good thing is that it's good to do SBM super efficiency. Okay, it's good to do SBM super efficiency because the advantage here, and by the way, your goal, this is one disadvantage of this method, by the way, Emily, some time ago we were talking about it, that it also tries to increase the efficiency of the inefficient ones.
Yes, Doc.
And the reason is because it was not designed for the inefficient guys. So when you want to run it, don't consider the inefficient guys. Of course, you get a result for them, but focus on the efficient guys because the whole super efficiency was designed for efficient guys. So focus on the efficient guys. And the good thing is that the SBM, when you just focus on the efficient guys, you will notice that it is discriminating more than the DEA super efficiency. For example, we want it to be higher, but it brought it lower for this, He brought it lower for that. He brought it lower for this. So that, so, yes, go ahead.
I think the last time the conclusion was that we used the super efficiency SBM when you had your DEAs were mostly efficient. So if you had a lot of ones in your DEA for the efficiency score, then you use the super efficiency one to differentiate between them.
Correct. That is true. So the whole idea is for the efficient firms. That's the main idea. And the DEA is still more discriminatory in the super efficiency world. The SBM is still more discriminatory in the super efficiency world than the DEA. You know, in both the super efficiency and non-super efficiency world, it is. Okay. So, ladies and gentlemen, these are the important things that you need to know about DEA and SBM and super efficiency models. And that brings us to the end of the entire caboodle.